Alright, welcome back guys. We're going to be looking at some of the support material for section 9.2. And you guys will probably remember that we've mentioned this in class, rational functions. We're going to be looking at solving rational equations for the first part of this material. So basically, a rational function or rational equation, it involves a fraction, okay? And typically there's a variable in the denominator of that fraction, so in the bottom of the fraction. And if you look here in the notes, it says we're going to try to eliminate these fractions from the equation by multiplying both sides of the equation by what's called the least common multiple, but this is also called the least common denominator, so you guys may have heard some of this terminology before. There's an example right here. This is what we call a rational equation. Okay. Remember, anytime it's got an equal sign in it, like this is an equation. This is not an expression. And so, you know, we'd still be looking for a value of x that'll make the left side equal to the right-hand side. Well, how do we solve one like this? We can't solve it the way we solved some of those equations in 2.1. So the first thing we're going to do is to clear the equation of fractions. We're going to multiply all the terms on both sides by the least common multiple, or the least common denominator. So in this example, our denominators are x minus 1 and x plus 1. So these denominators, guys, are what we call binomials because they consist of two terms. So typically when you have two denominators and they're just two different binomials, the least common multiple or the least common denominator is just going to be one of each of those. So it's going to be an x minus 1 times an x plus 1. Okay. And so what we'll do is multiply both sides, both of these fractions, by this least common multiple. So this is the way I typically show it. I put that first fraction in parentheses, and then we multiply it by the least common multiple, which is the product of those two binomials. We'll bring down our equal sign, and then we'll do the same thing for that second fraction. Put it inside parentheses and multiply it by that same least common multiple or least common denominator. See, as long as we're doing the same thing to both sides of the equation, it's going to stay balanced. But the nice thing about this, guys, is that it's going to allow us to divide out these denominators. So when you're looking at this, you want to look at these two factors, x minus 1 times x plus 1. These are understood to be in a numerator. And then this x minus 1 down here is in a denominator. So you can divide those out because those factors are exactly the same. This is the same binomial, x minus 1 over x minus 1. So to divide those out, typically I just draw a line through them. You can also say you're going to cancel them out by Kim. And now what we do is we multiply what we have left. So we have a 2 left over and we have this binomial left over. So I have to multiply this 2 to that x plus 1. So to do that, you use the distributive property. You multiply the 2 to both of those terms. So 2 times x will be 2x, and then 2 times 1 will be 2. So you put plus 2, bring down your equal sign, and we'll do the same thing on the right-hand side, except now it's the factors x plus 1 that are going to divide out. So I can cancel those out. Or, well, I like to say divide them out. Okay, divide those out, and then we'll multiply what's left. So we've got this x minus 1 right here times 3. So again, you're going to distribute. 3 times x is 3x, and 3 times negative 1 is negative 3. And that takes the fractions out of this. We no longer have fractions. And so we can solve this equation. What we've got to do is we've got to try to get the x by itself. So I'm going to subtract 3x from both sides. So I want my x over here on the left, although technically it doesn't really matter. So on the right hand side, 3x minus 3x is 0. That's going to leave us with that negative 3. Bring down the equals. And then over here, these are like terms, so 2x minus 3x is negative 1x. I didn't do anything with the plus 2, so I'm going to bring it down. And we'll have to recopy this up here so I've got enough room. Oops. And so now what we need to do is get this variable term by itself. So we need to eliminate the plus 2. So to do that, I'm going to subtract 2. 2 minus 2 is 0. That leaves me with negative 1x is equal to 3 minus 2 is 1. And the last step, guys, we've got to divide both sides by negative 1. So these negative 1's divide out. And that's going to leave us with x is equal to negative 1. Okay. Now what we have to do, if you look back, or if you look at this box right here, anytime we have a rational equation, or in other words, anytime we have an x in a denominator, we need to check our answer. Or we need to check our solution. Because if you guys remember from us talking about the domain of a function, we don't want these denominators to become zeros. So if I take a supposed solution and plug it back in for x, if either one of these denominators becomes 0, then we have to discard that solution. Okay, so let's check this one. So to check, you basically rewrite the equation, but you plug negative 1 in for x. Okay, and you see if you get the same number on both sides of the equation. Well, down here, negative 1 minus 1 is negative 2. So that gives us 2 divided by negative 2 is equal to 3 on the other one. And then negative 1 plus 1, this is problematic because those are opposites and they're going to give us 0. So guys, we're getting a 0 in the denominator. And what this means is that the solution that we came up with, negative 1, when we try to check it and plug it back in here, we get a 0 in the denominator. So that means that negative 1 is not the solution. So what I do is I exit out, say that's not the solution. Well, that's the only number we came up with. So that then means that this problem has no solution. Okay, so this, you can read this. This kind of walks you through that. It just basically says, check to see whether a number makes the denominator 0 in the original equation. If it does, it is not a solution. So negative 1 turns out not the solution, which means there is no solution to this particular equation. Guys, I realize I made a mistake. I miscopied a number. I was wondering about this one. The steps that I took were correct. However, having miscopied that number, guys, have made the results inaccurate. Okay, so I'm going to show you. So, you got to be careful. Take your time, because if you miscopy one number, you can end up getting the whole thing wrong. It's right here. When I recopied this equation from what I had down here, I have a negative 3 down here, which I've dropped down. But if you look over here, I never wrote the negative. I just put the 3, okay? So that's why this didn't work out. Now let me change that to a negative 3. And so now if I subtract 2, I'll get negative 1x is equal to, that's going to be negative 5. And then when we divide both sides by negative 1, we're going to get x is equal to positive 5. And this solution will work. We can still check it. I'll check it down here. Okay, so just plug into your original equation. So 2 over 5 minus 1 is equal to 3 over 5 plus 1. Yeah. Well, 5 minus 1 is 4, so 2 over 4 is equal to 5 plus 1 is 6, 3 over 6. And guys, this is actually a true statement, okay, because these fractions actually represent the same number, 1/2. If you were to actually reduce or simplify both of these fractions, you'd get 1/2 on both sides of this equation, okay. So that means that 5 is the solution. But you should, you should always check. All right, let's move on. Let's look at another one. This one's very similar. This is another rational equation, simply because it's got fractions in it, okay? And you can see we've got another variable in the denominator here. So the first thing we want to do, if you go back up and look at these steps, we want to try to get rid of those fractions. So we're going to multiply both sides of this equation by the least common denominator, or least common multiple, however you want to say it. Now let's look at this. These denominators are 3 and y. So similar to the last one, the least common denominator is going to be 1, 3, and 1, y. Okay? It only gets a little more challenging when your denominators are just all numbers. So my least common denominator is going to be 3 times y, which I can write as 3y. You really can't go wrong by taking one of each of these denominators and make that your least common multiple. Sometimes it won't be the least common multiple, but it will be a common multiple. So as long as it's a common multiple, it will work. Okay, so what we need to do is take 3y and multiply it to both sides of this equation. So I do it similar to the way I did that last one. Keep my fraction in parentheses. Other fraction in parentheses, multiply it by 3y. And again, we should see some stuff divide out. That's what eliminates these fractions. And in this case, it's this y that's in the numerator divided by this y in the denominator that we can divide out. And so again, what we're left with is this 3 times this y plus 2. So to multiply those, we have to use the distributive property again. Okay. So the 3 times the y would give us 3y, and then the 3 times the 2 is going to give us 6. Now on the other side, guys, the 3's will divide out. Leaving us with the 5 times the y. And 5 times y is 5y. Okay, I'll rewrite this one again. Now, we got rid of the fractions, so now we got to get the y by itself. Now look here, it really doesn't matter what side of the equation you get the y on. Since I already have a y on the right hand side, I'm going to try to get rid of the 3y that's on the left. So since this is a positive 3y, I'm going to subtract 3y from both sides. So right here on the left, 3y minus 3y is 0. That's just going to leave us with 6 equals, and then 5y minus 3y is 2y. Okay. Now, guys, you could have subtracted 5y to begin with, but that would have added another step, because you would have had your y term on the left. Your constant term would also be on the left, so then you'd have to turn around and move it back over to the right. So by choosing to put my y's on the right, that saved me a step. But there's no wrong way to do this. So now to get the y by itself, since it's getting multiplied by 2, we're going to divide both sides by 2. So these 2's are going to divide out. 6 divided by 2 is 3, and so y equals 3. And you could check this one as well. I'll show it up here real quick. So go back to your original equation and plug 3 in for those y's. So 3 plus 2 divided by 3 is equal to 5/3. Well, 3 plus 2, guys, is 5, so you get 5 over 3 is equal to 5 over 3. So that's true. So that means that 3 is the solution. Okay. All right, so now we're going to shift gears a little bit, and we're going to talk about what are called square roots and cube roots. So we cover a lot of ground in this support material, guys. A lot of this stuff I cover in another course that I teach called Transitional Algebra, and we spend the entire course just going over all this stuff. But in College Algebra with Support, there's not enough time, so we just have to try to cover what's absolutely necessary. Cover, what we can at a minimum, because we just don't have enough time. Okay, so now we're going to be looking not at rational equations, but at what are called radical equations. These are equations that contain what are called square roots or cube roots. Okay, and we're going to talk about these. So let's discuss these. They're called radicals. A square root and a cube root are called radicals. So it says this symbol right here, and I'll show you this in the calculator. It's right here above the x squared key. It's in blue. So if I were to turn this calculator on, hit second, and then that x squared key, you can grab that. This is the square root, by the way. But anyway, so this is called a radical, and usually any expression that has this symbol in it is called a rational expression. So let me define a couple things. I'm going to make something up here. Let's say I draw a radical, and I'm going to put a number underneath it, 64. So the radical is just the symbol. 64 is what we call the radicand. That's what's underneath the radical. And then sometimes, guys, there'll be a little number written. If there's not a number, this radical is understood to be a square root. But if there is a number, like if there were a 3 right there, this is what we would call a cube root. So if there is a number there, sometimes there will be, sometimes there won't, that is what we call an index. So if there's a 3, it's going to be a cube root. If there's not a number, it's understood to be a square root. All right, so let's talk about what a square root is. Here's the definition. It says the number c is a square root of a if you can square c, or in other words, raise it to the second power and get a. So think about this. The square root of 16 is 4. The reason I know that is because I can square 4. 4 to the second power is 16. Or the square root of 9 is 3. Because if I square 3, I get 9. And, we could go on and on. The square root of 100 is 10. Because 10 to the second power is 100. Okay, so to denote that you're taking a square root of some number, you use that symbol. Okay, so if I want to show the square root of 16, I put a 16 under there. So this is understood to mean the square root of 16, and then you could put the answer over here is 4. The square root of 16 is 4 because if you raise 4 to the second power, you get 16. Or, again, we could say the square root of 9 is 3, because as you saw over here, 3 to the second power is equal to 9. Let's do one more. The square root of 100 is 10. Okay, because 10 to the second power is 100. And here's a list of some square roots right here, guys. So you can see here, square root of 169 is 13. That means that 13 times 13 is 169. Square root of 25 is 5. Square root of 36 is 6, etc. Your calculator will do these as well. So I've got the square root key in there. If I put in, say, 36 and hit enter, it'll tell me it's 6. Okay, now what about a cube root? Cube root is very similar. A cube root, it says the number c is said to be the cube root of a, and it's written like this. If the third power of c, or in other words, if you can raise c to the third power, or cube it, and you get a, and that means c is what we call the cube root of a. So let me give you some examples. So with cube roots, guys, you're going to see an index. There'll be a little 3 sitting right there. This is how you know that it's a cube root and not a square root. Alright, so let's think about one. The cube root of 8. See if we can figure out this. Well, that would be a number that when we raise it to the third power, we get 8. Well, you could try this in your calculator. You say, well, what number to the third power would give me 8? So you could try maybe 3 to the third power. 27, that's too big. So let's go down one. Let's try 2 to the third power. That's 8. So this means the cube root of 8 is just the number 2. Okay. So with square roots, you're thinking about what number do I need to square or raise to the second power, but with cube roots, it's what number do I need to cube or raise to the third power that gives me this radicand right here. Let's do a couple others. Well, let me put here because 2 to the third power is 8. Okay. What about the cube root of, let's do 27. Well, we saw this one on the calculator. It's just 3. Because 3 to the third power is 27. And you could check this. Okay. The cube root of 64. So if you're not sure, you just try. We know 3 to the third power is 27. So then we would try 4 to the third power. And it's 64, so that means the cube root of 64 is just 4. Okay, because 4 to the third power is 64. And guys, this process would continue. We could do the cube root of 125, and that'll be 5. Because 5 to the third power is 125. Okay. So that's the difference between cube roots and square roots. And by the way, you do have a cube root operator in your calculator. If you come over here to math and go down to number 4, hit enter, and put in there, say, 125, it's 5. Okay, so you can verify this. Alright, so that's what square roots and cube roots are. The reason we go over this is because the last thing we're going to do is we're going to solve these radical equations. So these are equations that are going to have either square roots or cube roots in them. And so we have to solve for x. So many times what you're trying to do is you're trying to get rid of the square root or get rid of the cube root. Because normally, guys, there's going to be a variable under those radicals. All right, and we're going to use this principle of powers. Okay. This just basically says, just like we did with those rational equations when we multiplied both sides by the same least common multiple, we can raise both sides of an equation to the same power. As long as we do it to both sides, the equation is still going to stay equal or balanced. So that's what this principle of powers tells us. Alright, so these are the steps. It says, step number 1, we want to isolate the radical on one side of the equation. So in other words, we want to get the radical by itself. So get the square root or the cube root by itself, whatever the case is. Step number 2, raise both sides of the equation to a power to eliminate the radical. So what happens here, guys, is if we're trying to get rid of a square root, we square both sides of the equation. And if we're trying to get rid of a cube root, then we cube both sides of the equation. And then the last step is you want to check your solution again. Okay? And I put down here, the reason we want to check is because we cannot take the square root of a negative number. We didn't really talk about this, but if you try to take, for example, the square root of negative 4, well, that's not a real number. Okay? Because there is no number that when you square it gives you a negative. Now there is a number that when you square it will give you a 4, but not a negative 4. Okay. And if you're not sure, you can check. You could try, if we square 2, we get positive 4. What happens if we square negative 2? We still get positive 4. Because negative 2 times negative 2 is positive. Okay? So that's why we want to check. We don't want to have a negative number under the radical. Alright, so here's an example of a radical equation. You can see it's an equation that has a square root in it. Or here's another one. This one's got a square root in it. And in both cases, you've got an x underneath that radical, or underneath that square root. So when you're trying to solve these guys, you're trying to find a value for x, or a number for x, that would make the left side become equal to the right-hand side. Alright, so let's try to solve some of these. Example 3. This is definitely a radical equation because it's got this one big square root on the left. Now if you look above, the first step is to isolate the radical on one side. Well, let's look at this one. The radical, this big square root, is already isolated. When I say isolated, guys, I mean by itself on that side. So in this case, that's all we have on the left side. So the radical is already isolated. Okay. So then step number 2 says raise both sides of the equation to a power to eliminate the radical. So if it's a square root that you're trying to get rid of, you're going to square both sides of the equation. If it's a cube root, you're going to cube both sides. This is like doing the opposites again. The opposite of addition is subtraction. The opposite of multiplication is division. The opposite of taking a square root is actually squaring something. Okay, so this is the way you typically show it. You're going to take the left side, put it in parentheses, and you're going to square it. That just means give it an exponent of 2. And then you're going to take the right side, keep it in parentheses, and square it as well. See, we're doing the same thing to both sides of this equation, so it's going to stay balanced. Now, the nice thing that's going to happen here, guys, is that when you square a square root, you're left with just the radicand. Okay? Or in other words, the square root here gets canceled out. So I typically just kind of draw a line through those, through the square root and also the power of 2. Because all we're going to have left is whatever's underneath that radical. See, we've got to get rid of that radical to get access to the x in order to be able to solve this equation for x. Now I want to show you why these cancel over here. So if I had the square root of 25, well, let's do something a little easier. Say the square root of 9. Well, we know the square root of 9 is 3. So I've got the square root of 9, and I want to square this. So we could evaluate this. We could say, well, the square root of 9, like I said, is 3. And then you would have that same exponent. And 3 to the second power is just 9. So if you look right here, when you square a square root, you're left with just what's under that square root. Okay? So that's what I'm trying to point out here. That's the key takeaway. But we need to square the right-hand side as well. 7 to the second power is 49. Okay? And guys, once you've got rid of the radical, solving this equation should be pretty straightforward. We need to subtract 2 from both sides. So we're going to have 5x is equal to 49 minus 2 is 47. And then we're going to divide both sides by 5. And so this will yield x is equal to 47/5. Now this is a fraction, and furthermore it's a fraction that cannot be simplified. Okay. Now my last step would be to actually check and see if this is in fact the solution. So what I do is I go back to my original equation and I plug in 47/5 for x. And we see if we get a true statement here. Well, you have to start underneath the radical. 5 times 47/5. You could do this in your calculator, guys, but notice we have a 5 in the numerator and a 5 in the denominator. So why not just divide those out like we always do? And so we're left with just a 47 plus a 2, whoops, is equal to 7. 47 plus 2 is 49. So now we're left with the square root of 49 is equal to 7. And that is a true statement. The square root of 49 is 7. So we get 7 is equal to 7. Okay, so this verifies that 47/5 is my solution. Alright, let's try example 4. Now example 4, we've got a square root in it. Our first step, we've got to isolate that radical. So now this one's slightly different because this minus 4 is not underneath the square root. So we need to get just the square root by itself. So that means we need to eliminate the minus 4. So to do that, first let me rewrite this equation over here. Square root of 3x minus 4 is equal to 6. So to eliminate that negative 4 or minus 4, we're going to add 4 to both sides. So this will leave us with the square root of 3x is equal to 10. Now that we've got the square root isolated on the left, we can now square both sides of the equation because this is a square root. So remember, let's write it like this. Let's keep it in parentheses and then square it. The same thing for the right hand side. So again, guys, when you square a square root, you're just left with the radicand, or what's underneath the radical. So that just the 3x is equal to, but then on the right hand side, when we square 10, 10 squared is actually 100. Okay, let me pick this up over here. And we got rid of the square root, so now we can finally solve for x. We're going to divide both sides by 3. So this is going to give us 100 thirds. This is another irreducible fraction. Okay, but again, I need to check this. So I'm going to go back to my original equation. I'll plug in there 100 thirds for x. And then minus the 4 is equal to 6. Alright, well, underneath this radicand, again, we've got 3 times 100 thirds. We can divide out those 3's. Which will leave us with just 100 there, square root of just 100 minus 4 is equal to 6. And the square root of 100 is just the number 10. So guys, this looks like we're going to get a true statement because 10 minus 4 is 6. And so we have 6 is equal to 6 on both sides. So that confirms that 100 thirds is the solution. All right, let's look at a couple more. Now we're going to be working with a cube root because there's a little 3, an index of 3 here. So we have the cube root of x is equal to negative 5. The procedure is the same. We've still got to get the radical by itself. Well, it's just the cube root of x. It's already by itself on the left-hand side. So now we need to try to raise both sides of this equation to the same power. But we're not going to use the second power because this is not a square root. This is a cube root. So guys, the opposite of taking the cube root of something is cubing it. So we're going to cube both sides of this equation. I'm going to write it the same way. Let's keep the cube root of x in parentheses, and then we'll cube it, and then we'll keep the negative 5 in parentheses and cube it as well. So just like we saw with those square roots, when you cube a cube root, you're left with just the radicand, which in this case is just x. Bring down your equal sign. But then we need to cube negative 5. So this means negative 5 times negative 5 times negative 5. We could use our calculator to help us. I'll put in there negative 5, raise it to the third power, hit enter, negative 125. Okay. And that's it, because it's already solved for x. The x is already by itself. Now you may be wondering, why did I go ahead and circle this without checking to see if it's a solution? Well guys, if it's a cube root that you're working with in your equation, you don't have to check. It's only the square roots. Put this in the notes. Because with a cube root, it's okay to get a negative under the radical. Because you can actually take the square root of it, you can actually take the cube root of a negative number. It's just another negative number. Alright, let's try this last one. This is another cube root. And if you look at it, it's already by itself. That's all we have on the left-hand side, is that cube root of x minus 2. Okay? So since it's already by itself, guys, we don't have to isolate it. It's already isolated. But we do have to eliminate the cube root. And again, to do this, we're going to cube both sides of the equation. Okay? So again, when we cube a cube root, we are left with just the radicand, which is x minus 2 in this case. And then on the right-hand side, 3 cubed, that would be 3 times 3 times 3, which is 27. Okay. And the last step here, to isolate for x, we're going to need to add 2 to both sides. So we'll be left with x is equal to 27 plus 2, which is 29. I know this is the solution. I don't need to check it again because this is not a square root, but a cube root. Okay. So guys, I know I went kind of fast through this, but I didn't want to make it like an hour and a half. I just kind of wanted to go through these. Let me know if you have any questions.